Hi, this is Steve Denenberg. In this series of videos, we will be talking about work and energy. The kinetic energy of a mass in motion is 1/2 times the mass times the velocity squared. We could say the speed squared because kinetic energy is a scalar. It is not a vector. It doesn't have a direction to it. Kinetic means moving. And the kinetic energy of a particle is either zero or positive. It's never negative. The units of kinetic energy, surprising, are the units of mass times velocity squared. So that's kilograms times meters per second squared, or kilogram meters squared per second squared. And those are the units of energy. This is the definition of a joule, abbreviated J. Now, what is potential energy? Let's say you have a mass sitting on the edge of a cliff. Give us a little curve down there. There's no kinetic energy, but the mass rolls off, and under the force of gravity, it comes down, and now it's got some significant speed to it, some kinetic energy where it had none before. Is there something there? Yes, this mass had potential energy that was then converted to kinetic energy. And the potential energy that this mass had was mg times its height above the ground on the cliff. We'll discuss later why it is mgh. But the mass times the gravitational field times the height above the ground times the height above the reference plane is the potential energy that this mass has. And when the mass fell, that potential energy was turned into kinetic energy. Now its height is zero, and it lost all its potential energy, but it turned into kinetic energy. What are the units of this potential energy? Well, it's mass, which is kilograms, times the acceleration of gravity, and that's meters per second squared, times the height, and the height is in meters. Aha! Look, this is also in joules. It's the same exact units. Potential energy is also a scalar. It does not have a direction, and it can be negative. So let's find this on our page of equations for the AP Physics exam. The kinetic energy of a mass in motion is 1/2 mv squared. And the potential energy of that mass on the cliff is mg times delta y, which is our height. Now there's a little g subscript here. That means we're talking about the gravitational potential energy, the potential energy that this object had specifically because of the gravitational field, and we'll talk about that more too. So we have our kinetic energy, and we have what we are now calling gravitational potential energy. And these are both mechanical energy as opposed to thermal energy or chemical energy. We will also see that there is potential energy that can be stored in a spring, and we will call that either elastic potential energy or spring potential energy. The formula page said potential energy is abbreviated U, and the subscript G meant gravitational. We will also see potential energy of a spring when we study springs. So the kinetic energy and these two kinds of potential energy, the gravitational potential energy and the spring potential energy, sum to the total mechanical energy of a system. Sum to the total mechanical energy of a system of an object and the Earth. The Earth must be part of the system to provide the gravity for the gravitational potential energy. If you don't have the Earth as part of the system, you don't have gravity and you don't have gravitational potential energy. The total mechanical energy of a system will stay constant unless there are external forces operating on the system from outside the system, or unless there are non-conservative forces that steal energy away from the system, such as friction. Now let's take another look at that mass falling off the cliff again. So we have the height h of the cliff, and we have the mass that's going to drop from up here where it has its gravitational potential energy, but it's going to fall with the acceleration of gravity. And we want to figure out its velocity when it hits the ground. We've done this before when we were studying this equation, distance equals 1/2 at squared. Well, let's use that. So the height is 1/2, the acceleration is that of gravity, t squared. So we have t squared equals 2h over g, and t equals the square root of 2h over g. And something's velocity equals its acceleration times the time that it was accelerating. So if we multiply the time times the acceleration, we have the velocity equals gt, which is g times the square root of 2h over g, which equals the square root of 2hg. Okay, well, let's work that problem again using the potential energy of this block being turned into kinetic energy. When we're working energy problems, we always start with two equations. We always start with the energy initial equals the energy final. Now, if we know about work that's being done onto the system or friction taking energy away, we'll adjust this. But here we don't have that, and we always start with this, and then we always write the next line. The kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. If you write these two down, it'll save you a lot of trouble later on. So what do we have? The initial kinetic energy with the mass sitting on the top of the cliff is 0. The potential energy is mgh. The kinetic energy when it hits the ground is what? 1/2 mv squared. And the potential energy when it hits the ground is down to 0. So we have mgh equals 1/2 mv squared. The m's cancel out. We have v squared equals 2gh, and v equals the square root of 2gh. Same thing. And it was a bit easier to do. If you can use energy methods to solve your problems, usually it's going to be a bit easier. Let's take a similar situation. We have a mass that's going to fall off the cliff, and it's going to swoop around, and there's a hill and another hill, and it's going to go back down, and another hill, and then it's going to head up. And our question is, how high is this mass going to get before it finally runs out of kinetic energy and stops? Well, if there's no friction along the path, and there's nobody pushing back on it, then nothing is stealing energy away from this mass. The mass will come down, turning its potential energy into kinetic energy, and then it'll head up a hill, lose a little kinetic energy, and gain a little potential energy. And the potential energy, kinetic energy dance will continue. And then how high will it get when it finally comes to a stop, when it loses all of its kinetic energy? Well, if there's no friction to steal energy away, it'll get right back to the same h, where it will have a potential energy of mgh again. It can't get higher because then it would have too much energy. In this situation, the total mechanical energy is not going to change. We said the first equation we write down is energy initial equals energy final. And its total mechanical energy here is mgh. So when it finally runs out of kinetic energy, it's going to climb to mgh again. If there is friction along the way, then it's going to lose energy as it travels, and its total mechanical energy will be less than this. and it will end up not as high when it runs out of steam and stops moving. Now let's look at it yet again, but this time we're going to start with some kinetic energy. So here's our starting point, distance h off the ground, and the mass is going to come out of the gate here with the speed of v sub naught. It's going to do the same thing. It's going to gain more speed, more kinetic energy, as it loses its gravitational potential energy. And then it's going to climb, and it's going to climb, and it's going to come to a stop. But this time, I think it's going to get higher than h when it stops, because it started with a gravitational potential energy of mgh, and it also had some kinetic energy of 1/2 m v sub naught squared. So its total mechanical energy was more than just its gravitational potential energy. But if it climbs until it stops, until there's no more kinetic energy, then all of its mechanical energy will be in gravitational potential energy, and it'll be higher than h. Well, let's see how it works. How do we start these problems? The initial energy equals the final energy. The initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy. I like writing these two. Then you just have to fill it in. The initial potential energy was its mgh because it was h above the ground. The initial kinetic energy was 1/2 m v sub naught squared because it started out with the speed of v sub naught. The final potential energy is mg times its final height, times how high it climbed before it stopped. And its final kinetic energy is 0, because we said it stopped, and it's not moving, and it doesn't have kinetic energy. So now let's run through this. We have mgh plus 1/2 m v sub naught squared equals mgh final. Let's call this h initial. We'll give it an h sub naught. Well, the masses can go because they cancel out. And the reason they often cancel out is because the potential energy is proportional to the mass, and the kinetic energy is also proportional to the mass. Gravity doesn't cancel out because the potential energy is proportional to the gravity, but the kinetic energy is not proportional to the gravity. But so let's isolate the final height, which is what we want. So gravity times the initial height plus 1/2 the initial velocity squared equals gravity times the final height. So the final height equals gh sub naught plus 1/2 v sub naught squared all over g, which equals h sub naught plus v sub naught squared over 2g. Well, look at this. The final height is going to be the initial height plus an additional term. And that's what we thought was going to happen. We started with some kinetic energy with v sub naught, but up here when it came to rest, we turned that kinetic energy into potential energy, and it allowed the mass to climb a little bit higher. And this is how much higher it was allowed to climb. Does it make sense? Well, look at this. We have gravity in the denominator, and that makes sense because if we're in a more powerful gravitational field, you would expect to not climb as high in using up the kinetic energy that it started out with, because the gravitational potential energy is proportional to the gravity. So if you're on a planet with much stronger gravity, you will need to climb a smaller height in order to acquire a certain amount of gravitational potential energy. Now let's go back to our diagram. We talked about how mass dropped out of the equation of the final height. So any mass coming in with this initial velocity and traveling this route is going to wind up at this final height. Now what else? What if we had the same basic problem, but the mass was launched with a speed of v sub naught at an angle this way, say a 30-degree angle? Will that change the height? Well, the angle didn't show up in the final equation, so the angle doesn't matter. What matters is how much energy it has at the start of its trip. It has the gravitational potential energy because it's h height above the ground, and it has kinetic energy because it starts out with a certain speed. But the angle of the launch won't matter in this situation. You can imagine what would happen if it launched with a certain angle. It would head up and gravity would slow its rise, and it would come back down, and it would have that same v sub naught right here. And look, right here, once again, it has 1/2 mv sub naught squared of energy plus mgh of gravitational potential energy. So if it can make these corners, it's still going to get this high. Oh, and one more thing. Since there's no friction, we can run it backwards too. We can start by placing a ball this high and let it run down and come back up, and when it gets to h, it will turn out to have a speed of v sub naught and a kinetic energy of 1/2 mv sub naught there. When we're looking at these situations, we often have a block on the edge of a cliff, and the block's going to do something. And we say it has potential energy mg times h, and h is this distance. Well, why are we measuring h from the block down to the ground? Can't we measure h down to a spot that's 8 meters below the ground? Well, in fact, we can. When we're looking at potential energy, we're only looking at the difference between the potential energy here and the potential energy here. And if we want to know how fast the block is moving here, we only want to know the difference between the potential energy here and the potential energy here. So if we say the ground is at potential energy 0, and the block starts out at a potential energy of h, we can do our calculations. Let's say h equals 10 meters. Okay, we can do our calculations. But if we said that the ground is at level 3,741 and the block starts out at level 3,751, our calculations would come out exactly the same. Because whenever we are working with potential energy, we're only talking about the difference in potential energy between two positions. The block moved this far down into the gravity well and liberated mgh worth of gravitational potential energy and got that as kinetic energy. Well, if h is 10, we could say that the kinetic energy that the mass has down here is equal to the gravitational potential energy decrease as it fell. So we went from mg times 3751 down to mg times 3741, and we'll get the same answer. And in fact, on that formulas page that you get at the beginning of the test, it reflects that, because it says the potential energy, the gravitational potential energy, what it actually says is mg times delta y, which means in our situation here, mg times the change in height. Not the absolute height, height above sea level, height above the center of the earth. It's only the change in height that's important. Now, you already knew that intrinsically. I'm just laying it out for you. So you set your reference plane somewhere where the calculations are easy. If we say the lowest point that the mass is going to hit, let's call that 0. And that makes our calculations easy. Easier than calling it 3741. All right, that was fun. Let's talk about work. Okay, you put someone in a storeroom. And the storeroom has some shelves. And it's got boxes on the middle shelf. And you tell the person, I want you to move all these boxes to the top shelf. Move them up here. And you go away. And you come back later. And the boxes are still sitting right where they were. And you say to the person, you didn't do any work. Well, you would be right. There was no work done because the boxes didn't move. Work is the transfer of energy from one object or system to another. The transfer of energy. Work happens when you apply a force to a mass and you move it some distance. You need to have a force applied to a mass and it has to move. The work is the magnitude of the force times the distance that the mass moved. If there's no movement, there's no work. So the worker now tells you, but I'm exhausted. I picked up a box and I held it for 2 hours and I sweated and sweated until I was exhausted and I put it back on the middle shelf. Answer, nope, no work, because the distance was 0. Doesn't matter how hard he thought he was working, no work done, as physicists call work. Okay, so here's our storeroom again. Here's our middle shelf. Let's say he did take a box and he moved it up to the top shelf. And he moved it up a distance h. How much work did he do? Well, work is force times distance, and the distance he moved it was h. What was the force? Well, the box has a certain mass, m. The force was mg. The force was the weight of the box, the gravitational force that he has to overcome to start the box moving. So the work that he did turns out to be mgh. Aha! Do you recognize that from somewhere? mgh is the potential energy, the gravitational potential energy that a mass has in a gravitational field if it's a height h above the ground, our reference plane. So that means if you have a mass that's sitting on the ground and you raise it to a height h above the ground, you've moved it a distance h against a force of mg, and you've done this much work to the mass. But that looks just like potential energy, and indeed this is. This is the units of energy. Work has units of energy. Let's see what it is. Work equals force times distance. Force equals ma, that's how I think about the units, times distance. So that's mass, kilograms. Acceleration is meters per second squared times distance. Here we have, just like mv squared, which is kinetic energy, work and gravitational potential energy and kinetic energy, and as we will see, spring potential energy all have the same units, joules. This system right here, where you had a mass on the ground and you raised it up to the top, this system started with no mechanical energy. There was no potential energy and there was no kinetic energy. And after you raised the mass up here, now its total mechanical energy is in its gravitational potential energy, mgh, which is the work that you did on the mass. The work that is done on an object or a system adds to the total mechanical energy of the system. That's what we did here. We did work on the mass and we added to the total mechanical energy of the system, because the gravitational potential energy is part of that total mechanical energy. In the next video, we will continue our discussion of work and energy.